going to give us an interesting talk today. He is an associate professor of mathematics at University of Tennessee, Knoxville. He received his PhD from Texas A&M in 2010. And then he joined the University of Maryland as a postdoc, where he was the postdoc there from 2010 to 2013, and joined the University of Tennessee, Knoxville in 2013. And he has very interesting work on various topics, but his interests especially are in numerical analysis of PDEs and especially non-local PDEs. Well, Abner, we look forward to listening to your talk today. Please go ahead.
Well, thank you very much, Mohammed, for the invitation. Yeah, so it's interesting to give talks in this new format, talking to a screen. But I will keep my eye on the chat and interrupt me at any moment if there's any questions. So what I will talk about today is some joint work that I have been doing for the past maybe year or so with my postdoc Wembley. So by the way, if in a couple of years you guys are hiring, keep an eye for this guy. He's very sharp, very bright. So what we have been doing is trying to do some theory and numerics for time fractional gradient flows. So this is a little outline of the talk that I will give today. So first, I will try to motivate the problem and try to see what's the possible applications or why it is that I want to do what I'm doing. And then both for the theory and for the numerics, I'm going to go through a very nice, if you want, parallel between the classical case of gradient flows and the fractional case of gradient flows. So when talking about classical gradient flows, I will try to extract the essential pieces of information so that allows you to get a theory of existence, uniqueness, or some regularity properties of the solution, and try to see what needs to be done to accomplish the same key and crucial steps in the fractional case. So that will be both for the theory and for the numerical analysis of the problem. I will give some numerical illustrations of the schemes that we developed, and then I will conclude. So as a matter of introduction and motivation, I think that everybody has heard about non-local problems, fractional derivatives these days. The reason for that is partially because, well, of course, they're mathematically interesting, um, but also because many practitioners have realized that they have become useful to describe processes that have memory, processes that have uh, different scales. So for instance, if there's an overlapping between microscopic and macroscopic scales, if there's long range interactions on and many other effects. Uh, a classical example of where these fractional derivatives and integrals have appeared is in the case of anomalous diffusion. So classical diffusion is usually represented by the heat equation, right, which we've all seen before. Um, and classical diffusion is sometimes characterized by the fact that there's a very particular scaling between space and time, namely that's, well, the mean displacement squared scales like time. And that kind of, in a sense, explains why this relation one time to two space explains why in the heat equation you see one time derivative versus two space derivatives. Right? Of course, this is a very rough explanation, but at least heuristically, that can be an explanation. However, it has become apparent that there's many cases of anomalous diffusion. For instance, there's a super diffusive regime in which the scaling between time and space is not 1 to 2, but the time scales like some power alpha compared to space squared, where this alpha is a number larger than 1. This will give rise to some other type of problems, which I will not consider today. The problems of the form of the problems that I want to consider today are the so-called related to the subdiffusive case, in which you also have this same relationship over here, but with a power alpha that is between 0 and 1. So if in the classical diffusion case, the scaling 1 to 2 gave you one time derivative to two space derivatives, at least heuristically, it makes sense to say then that in the subdiffusive case, what you're going to have here is some derivative of order alpha between 0 and 1, and that is what we're going to call the Caputo derivative. I will define it later, but it will take us a little bit to be precise on the meaning of this operator, but just think of something that resembles a derivative that is of order between 0 and 1. And equations of this form are usually used to model memory effects, as we will see from the definition of this Caputo derivative. I want to see this equation, which I will call a time fractional heat equation, from a little bit of a different point of view. Namely, we all know that the Laplacian can be thought of as some sort of variational derivative of the Dirichlet energy. So the time fractional heat equation can be written or can be understood as well the Caputo derivative of U plus the derivative of this energy equal to some data. This, of course, can be generalized to the case, say, for instance, of the parabolic P Laplace problem, in which you consider not the Laplacian, but the P Laplacian, which is nothing but the variational derivative of this type of energy. So that's like the W1P semi-norm, right? And here, the P being larger than 1 is quite important, because in the case P equal 1, you get you need to be more careful, and you get something called you would get something called the TV flow or total variation flow, because now your space, your visible space of functions is not a space of subgroup functions, but of functions of bounded variation. So you need to allow derivatives to be random measures. And I only mention this because this equation, this so-called total variation flow, to be understood properly, because this is like an absolute value, so an absolute value of this derivative is not differentiable, especially at 0. So to interpret it properly, you need to be a little bit careful in the sense that, well, now you need to find a pair of objects, a function u and a vector field c, that are going to satisfy this pair of conditions. Of course, this needs to be carefully understood, because here you have a random measure and you need to be able to pair it with a vector field. So that needs some care, and especially in where this vector c is supposed to live. I don't want to get into the details of that right now. But one of the things that it's going to characterize this vector c is this inequality here, this variational inequality. Another type of examples of the problems that I want to talk about or I want to consider is some sort of ODEs or fractional ODEs with obstacle. So let's imagine that we have a very simplified pool table, if you want. So it's this gray thing is my pool table. Here I have my a ball that I hit, and if it doesn't hit the walls, so my pool table is the interval -1, 1, say. So if it doesn't hit the walls, the ball is going to move according to its usual law of motion. So it's going to be an equation like this one, right? Think of this being something like mass time acceleration equal the applied forces or something. Now, if it's going to touch one of the wall is going to exert a certain amount of force to the wall, but only enough so that the ball gets reflected, right? It's not going to push it, it's not going to pull it, it's just going to do enough so that the, the ball gets reflected. So say, for instance, let's consider one of the cases, let's say, like it's in the picture here, that the ball is moving in this direction, and it's going to touch the right wall. Well, first, if for some reason, maybe say you're a very good pool player and you put some English on the ball, then maybe it barely touches and by itself it's going to get reflected. So maybe its direction of motion is negative, then the wall doesn't need to do anything because the particle, this ball, is going to move left anyways. If this is not the case, that means if there wasn't a wall there, the ball would move ball would have kept moving, then what the wall is going to do is the following. Well, right before it touches the wall, the equation of motion is this one, where we can split the force in term, the force into the positive and negative part. And so being reflected means that now it's going to move only in the negative direction. So the wall is going to be doing so that the negative part, the F plus, is the positive part, sorry, the F plus is going to vanish. So the reflection is going to be expressed in this form. You can do a similar analysis for the left wall. And in short, what you're going to get is the following, that if your particle is positioned strictly between -1 and 1, then it moves according to this law of motion. However, if you're at the right endpoint, it's going to be, the forcing term is going to be equal to minus the negative part. And if you're on the left endpoint, the forcing is going to be equal to the positive part. I can, or we can succinctly write this as a differential inclusion. I will get to that in a little bit. Another example of problems that can be considered, or that I want to consider in this framework, are fractional parabolic obstacle problems. So, for instance, I can define in some function space a collection of functions that are above a given obstacle. This G is going to be an obstacle. So think of, yeah, this is an obstacle, and I'm just considering functions that are above it. And I'm going to consider a problem of given by these complementarity conditions. So the solution to this problem needs to be above the obstacle, and the product of these two objects needs to be equal to 0. So either I am touching the obstacle, or if this is strictly positive, then the second term needs to be equal to 0. That means that the function is solving an equation. This is equivalent to the following evolution variational inequality, which is yeah, a parabolic obstacle problem. This can also be written as a differential inclusion. And so I have come to the big generality by saying that, well, the type of problems that I want to consider are of the following form. Let's say that I have a separable Hilbert space. I need separability because, well, first I want to do numerics, and I don't know how to do that in a non-separable space, but also because of some measurability issues that may arise, and I will not mention them further. Um, on this space, I have a convex and lower semi-continuous energy. I have an initial condition, some forcing term, and I want to look at a differential inclusion of this form. So the Caputo derivative, which I have yet to define, of my function u, plus the sub-differential of my energy that contains the f and some initial conditions, right? Um, if alpha is here I have the Caputo derivative of order alpha, and so if alpha is equal to 1, this should reduce and does reduce to the classical derivative, and this is a classical gradient flow problem. Of course, it's one we all know very well that f being 0, this can be understood as steepest descent method to minimize your energy phi. And yeah, so of course, steepest descent is very classical, but not the most efficient method to minimize a function. So there are some others, and we have done some work on that. But the point is that I want to look at this type of differential inclusions, in which this is a Caputo derivative, and all the problems that I mentioned before can be cast in this framework. So let me now consider the classical gradient flow case, so the case when alpha is equal to 0, and trying to extract the essential points of the theory to see what needs to be done if I want to develop a theory for the fractional case. So let's remember I considered the classical case, so I replaced the Caputo derivative with just a regular derivative. And now I remind you that being in the subdifferential is equivalent to this inclusion. So remember the subdifferential It's just the collection of all the slopes of the planes that touch the graph of my energy from below. And this is what that means in formulas. So if I want to define a notion of solution for this problem, there's many ways of doing it, but the one that I like is the one that is convenient for what we're going to do, is the notion of energy solution. So we're going to say that a function that has suitable differentiability properties in time is an energy solution if, of course, it satisfies the initial condition. And then to show what type of equation this needs to solve, or what type of problem needs to solve, essentially what I'm doing is multiplying, taking inner product of this inclusion with u minus w, and using that this is the solve differential, so that I get essentially this evolution variational inequality. Right? So once again, going from this expression to the definition of energy solution is just using, well, essentially taking in product with u minus w and using the definition of subdifferential. One of the reasons why this is a good definition of solution is because right away you can get that energy solutions are unique. All that you need to do, and this is very easy, is, well, you assume that you have two energy solutions. You just write the variational inequalities that they need to solve, and then you just choose as test function in one equation the solution of the other one, or the one inequality. You can add them so that these terms will go away. These terms will go away as well. And here you're getting, when you add, the derivative of the difference times the difference. That is, because you're in a Hilbert space, the derivative, half of the derivative of the norm squared, and that is less or equal to 0. So the norm is a non-increasing function, but you start at 0 because they both start at the same point, the same initial condition, so they have to coincide. So this is a good, I guess, a good definition, because almost for free you get uniqueness of solutions. To show existence, you need to do a little bit more work, but still it's not so complicated. And one of the ways of doing it is what the Georgian, in honor of the Georgians, called minimizing movement scheme. So this is a somewhat constructive procedure that you can do to get existence of solutions. And the idea is the following. So you're going to discretize in time. So you're going to introduce a partition of time of, say, variable time step. The maximum one is going to be used with a bold. At each one of these times, discrete times, I'm going to introduce an approximation of the solution, this value. I'm going to call that capital U. And I'm going to find this approximation by minimizing this problem, finding the minimum of this problem. So forget about the F, that's not so important here. You have the original energy, and then you have this sort of regularization term that has to do with the time step, the local time step, and the previous solution. Okay, my energy was only assumed to be convex, but because I am in a Hilbert space and I'm adding the square of the norm, that's a strictly convex and coercive term. So this problem is going to have a unique solution. So that unique solution is what I'm going to call UN, my approximation with the solution at time Tn. And if you write the Euler-Lagrange equations for this minimization problem, that is actually equivalent to an implicit Euler discretization of this differential inclusion here. Right? So implicit Euler in the sense that I'm looking at backward time difference in here, or that I'm being implicit in this term over here. So we know how to construct these big U's, the discrete approximations. Now, those are given just at discrete instances of time. So we need to find a way to connect the dots, if you will. We need out of those discrete samples to construct functions that are going to be our candidates for objects that are going to be solutions, or at least that are going to, in the limit, be the solution. And we have essentially two obvious candidates, right? If we only have the values at the discrete instances of time, let's think of, we only have the blue dots here. What we can do is we can be, for instance, constant in each interval, each subinterval. So I'm just going to fill the gaps by using a constant to the left, sorry, and I move to the left to preserve causality. And that is the function that I'm going to denote from now on by a bar. So from discrete instances of time, I fill with a constant that is going to be my bar. That is one option. I have another option, but that is by connecting the dots. So by constructing a piecewise linear that in each subinterval is going to be obtained by just taking a convex combination of the values at the endpoints. That is my green function that I'm going to denote by hats. And we like this function because of two reasons. First, of course, because it's continuous. And second, because if we compute its derivative at any subinterval, we get exactly the expression that's you see here, that it appears in the optimality conditions for the minimizing movement scheme, right? So using these two functions, the u bar piecewise constant and u hat piecewise linear, I can write the minimizing movement scheme also as a variational inequality. Of course, it involves two functions now, but such is life. The important thing about it is that now I can play usual games. If, for instance, if I choose suitable test functions here, I can get some a priori estimates provided that my data is suitably chosen. I can get suitable a priori estimates that allow me to pass to the limits in this approximation. So to pass to the limits in the size of the partition. And uh, this allows me to show passing to the limit by compactness. I can construct an object, and it turns out that that object is a solution to our classical gradient flow. Well, but we also show that we have uniqueness. So we have an existence of uniqueness result that if your right-hand side is L2 in time, and you start from something that has finite energy, the classical gradient flow has a unique energy solution. This theorem, many incarnations, has been proved, for instance, by Rothe in the 30s, by Randall Liggett in the early 70s, and for instance, is found in the book by Bresis. Um, so I want to, like I said, the point of talking about the classical gradient flow is that I want to extract the essential steps that allowed me to get existence and uniqueness for this problem. And so I think that to develop this theory, there were three key steps. First one was that to get uniqueness, from the definition of energy solutions, we arrived at something like the difference of two solutions against the derivative of the difference of two solutions, and that bounds from above, sorry, some quantity. So an inequality of this form. To get existence, we needed two things. The first was some sort of minimizing movement scheme to get the approximate solution, the approximate values at the grid points. And the second one was suitable interpolation, so a way to, from here, from these values, discrete values, construct a function that first its derivative was piecewise constant, because that meant that I could plug it in to the equation that the minimizing movement schemes describes, and that allows me to get some estimates for these functions, and that with that I can pass to the limit. So let's see if I can do the same for a fractional gradient flow. And so before I do that, of course, finally, I can tell you what the Caputo derivative is. So for sufficiently smooth functions, the Caputo derivative is defined this way. What is it that we're doing here? We take the function, we differentiate it once, and then we integrate it 1 minus alpha times. So of course, morally, this derivative and this one over here are going to cancel, so I'm integrating minus alpha times or differentiating alpha times. To be precise, for sufficiently smooth functions, the way to define this is as follows. So you see that this is exactly why the people use this Caputo derivative to described memory, because what you're doing is taking a weighted average of the derivative for all instances of time. Of course, this definition is fine, but I claim that it is unnatural. And it is unnatural because we're trying to define a derivative of order alpha between 0 and 1, but to define differentiability of order less than 1, you're requiring that you have differentiability of order 1. So you're defining what a lower order objects in terms of a higher order one. That doesn't really make sense. And so a good question could be, well, is there a way to define the Caputo derivative for buffer functions? And it turns out that there is. I mean, there are several approaches, and the approaches differ in to what class of buffer functions can be applied. So, for instance, some approaches date back to the 1920s by Marceau and the so-called Marceau derivative that, for instance, can be applied to Helder functions. I only want to mention very quickly that this definition of Marceau, of derivative in the sense of Marceau, has been used by Caffarelli, Basurk, and Mark Allen in a series of papers on regularity for no-local diffusion equations. There is some, for instance, some other approaches by my colleague Xiaobin Feng and his students Mitch Sutton. But the one that we're going to use is the one that was proposed in a series of papers by Lei Li and Jiangu Liu, that I think they're your neighbors. That is essentially described as follows. So what you're going to do is you're going to flip the order of the derivative and the fractional integral, right? But of course, you're going to pay a price for that, and the price for that is paid by this sort of correction term. That is the initial value of W times the Heaviside function. And I see now that I have a typo here. This H and theta should be the same as the Heaviside function. So now this definition kind of makes sense even in the sense of distribution. So this can be applied even to distributions because they show that this operation form a convolution semigroup and some other properties. The point is that this definition makes sense for even a much more general class of functions. And so we are going to, this is the one that we're going to adopt. So the Caputo derivative.
Yes, question. Is the second definition the Riemann-Liouville?
This one over here?
Yeah.
It is the Riemann-Liouville, but the argument is not the function itself, it's the function minus the initial value.
Gotcha. Okay. Thank you.
Yeah, and that's a good point. That say some other people have defined some fractional derivatives also in this way. Say, for instance, there's several papers by Rico Sacher, I think, that's the way you pronounce his name, that he has studied evolution equations with fractional time derivatives, in which he writes precisely this, but he was never explicit in saying, okay, or at least from what I can remember, he was never explicit in saying why he was using this type of derivative. But yes, this is the Riemann-Liouville derivative, not of the function itself, but of the function minus its initial value, essentially. One of the good things that Li and Liu proved, for instance, is that under some condition on the function, its initial condition or initial value, and its Caputo derivative, you have a sort of fractional fundamental theorem of calculus that says that the function at any time is equal to the function at 0 plus the fractional integral of its fractional derivative. Right, so this is essentially like a fractional fundamental theorem of calculus, and we're going to be using this quite a bit. Okay, so this is our definition of the Caputo derivative. And now, from this definition right away, we can get what I call the key inequality, which is the analog of what allowed us to get uniqueness in the classical case. If you remember, in the classical case, we had the derivative of the norm square, which is something convex, is bounded from above by the inner product of the argument times the derivative of the argument. So in fact, for this definition of the Caputo derivative, we can prove, or it can be, they prove an analog of this, or generalization of this inequality, namely that if you have a convex function, in particular the norm square is convex, the Caputo derivative of this convex function is bounded from above by the subdifferential of the convex function times the Caputo derivative of the argument. That is exactly the analog of this expression over here. And so this motivates right away to define for the fractional gradient flow, which now I have a Caputo derivative in the sense that I just described a little bit ago, this differential inclusion. And so we can define for this problem energy solutions much in the same way that we did for the classical case. Namely, we're going to say that a function with some differentiability properties in time is an energy solution if, well, it satisfies the initial condition in a certain sense, and it satisfies this evolution and variation inequality, which is obtained exactly as in the classical case by essentially taking this inclusion and inner product with u minus w. We like this definition, once again, because using that key inequality, we can get uniqueness in a few steps. And the steps are exactly, with a little variation, the same ones that in the classical case. You assume you have two solutions, you compare their evolution variational inequalities, and you get exactly what bounds what you have on the right-hand side of the key inequality. Now you can use the fundamental theorem of, the fractional fundamental theorem of calculus for norm squared. And we have that, well, that quantity at every time t is equal to the fractional integral of its Caputo derivative, but that is bounded by something that is non-positive, and so this quantity is non-positive, so the two solutions must coincide. So very quickly and very easily, because of this key inequality, we can get uniqueness of energy solutions. Well, what about existence? So if we want to follow the same program, we need to find some sort of fractional minimizing movement scheme. And for that, we need a suitable discretization with the Caputo derivative. And so the one that we're going to, there's many around in the market, but the one that we're going to adopt is the following. So starting from our fundamental theorem of fractional calculus, let's pretend that the Caputo derivative of a function, my function w, is piecewise constant over my partition. Then, if I evaluate this function at one of the grid points, what it's telling me here is, I can chop this integral in my partition points. In each one of the subintervals, this is a constant, so it comes out, this kernel integrates, and we end up with a vector identity of this form, right? The values at the grid points are equal to, well, the initial value plus some matrix that has to do with the integration of these kernels, on each one of the subintervals of my partition, times the vector of piecewise constants that this Caputo derivative was assumed to be. Okay, this matrix, because we're integrating from 0 to t, right? We don't see into the future to compute the value of at time t. Is going to be lower triangular, and because I am integrating this kernel that is positive, the diagonals are going to be positive, so this matrix is non-singular as well. So what we're going to do to define the discrete Caputo derivative is just inverting that inequality that we got there. So the discrete Caputo derivative of a grid function, or a collection of grid values with respect to a partition, is going to be given by this expression over here. So we only need to know how to invert this matrix, and we only need to know properties of that inverse to be able to define a fractional minimizing movement scheme. And so it turns out that, for instance, if my partition is uniform, my matrix is going to be templates, and so matrix multiplication by this matrix can be thought of as a convolution of sequences. And so inverting this matrix can be thought of as deconvolution. And so in the literature, There's a lot of deconvolution schemes that are based on this idea. However, for reasons that I want to mention later, I do not want to assume that this partition is uniform. And so we need to do something else. We cannot use that the matrix is templates anymore or properties of convolution. What we can prove is that for any partition, it doesn't matter how I partition my time interval, um, the diagonal elements of the inverse are going to be positive, the off-diagonal elements are going to be negative, and there's some monotonicity with respect to rows. Right? So because of this, we can directly, by using the definition of the discrete Caputo derivative, get a discrete version of the key inequality, the one that allowed us to get uniqueness for energy solutions. And the proof again is it's just using the properties of this matrix and that it has certain signs in the diagonal and off-diagonal entries. With that having been obtained, remember these terms, the off-diagonal ones, are negative, so we can define a fractional minimizing movements in much a similar way as in the classical case. So again, forget about the f that only has to do with the right hand side. I have my energy, have the difference of my arguments and past values of u, and this is the analog now of the 1 over time step that we had. Remember, these guys were negative, so this is positive. So this, once again, is a strictly convex functional that we're trying to minimize, and so it has a unique solution. And its Euler-Lagrange equations turn out to be the same as if we were going to compute the discrete Caputo derivative over this partition of that sequence of values. So once again, this is an analog of, say, if you want, the implicit Euler scheme that the classical minimizing movement schemes led you to. And so if we follow the program that we had in mind before, we need to find an analog of this piecewise linear interpolant such that now it's not going to be piecewise linear, it needs to be something else, but in such a way that its Caputo derivative is exactly this expression over here. So it's going to be piecewise constant, and then each subinterval is equal to this expression over here. Well, we're just going to make it into existence if you want. We're going to define these phi I as functions that are, they are what they are, but the point is that it's their Caputo derivative is going to be 1 at an interval and 0 at all the others. And so I can define my u hat to be just a linear combination of these functions. And this is not a cartoon. This is actually how this u hat looks like. It's continuous, but not very smooth, especially at the grid points. But still, its Caputo derivative is going to be piecewise constant. And that's what we want. Because now we can say that this, which is the optimality condition for the optimizing movements, or the minimizing movements, sorry, can become this evolution variational inequality, which is with the fact that now you have a Caputo derivative instead of a regular one. It's exactly the same that you had in the classical case. So you can play similar games and play with some test functions to get some good estimates, a priori estimates, on the Caputo derivative of this interpolant. And of course, the a priori estimates are going to depend on your data. As expected, you need to start with something that has finite energy. And you have some other condition, not just that the right-hand side is in L2, but something extra that in fact is quite natural, and I can explain if I have time at the end. Well, the point is that we now have, again, enough estimates to pass to the limit. So if these guys are under control, then that's an a priori estimate that is independent of your partition, so you can pass to the limit. And assuming, again, that you start with something that has finite energy, some condition on the right-hand side, Then this fractional gradient flow problem has a unique, we already showed uniqueness, energy solution. And on top of that, as a consequence of the way that we prove things, we can also show that this energy solution turns out to be also Helder of order alpha over 2. And yeah, this is the first big result that we have with Webo in this direction. And uh, one good thing about this result is not only, of course, the existence and uniqueness, but also that in the classical case, in the classical gradient flow case, an energy solution is H1, which by Sobolev embedding is Helder 1 half. So we have this sort of continuity with respect to alpha. That's, I mean, for alpha derivative in time, your solution is alpha over 2. For one derivative, is 1 half. So with that being said, so we have an existence and uniqueness theory. So now we can try to approximate. So again, very quickly, let me try to go through the classical theory to see what are the essential points here. And the essential points of how to do an first and a posteriori estimate in the spirit of what Nocheto Savarian Verdi did in 2000 is to look at say the implicit Euler or the minimizing movement scheme in this way, or in the term of in the way of operational inequality. Now we're going to do something very clever. We're going to take everything to one side of this inequality, so that this inequality reads something is non-negative. And this something is going to be a quantity that is going to be important for us. First of all, because it's completely computable, it only depends on the data and the discrete solution. And on top of that, more importantly, using, and this is very important, using that the u hat, my piecewise linear, is a convex combination of the values at the grid points, I can play with this evolution variational inequality that the interpolant and the piecewise constant function satisfied to realize, well, here I had two functions. I want to get rid of these two functions and have an evolution variational inequality only for the u hat. And I can do that. And it turns out that it solves essentially the same evolution variational inequality that the exact solution solves, but with some extra noise. And this extra noise is exactly this quantity over here. So I can compare now the same way that I did when we proved uniqueness, this evolution variation inequality for the approximate solution and the one with the exact solution, to get what is known as a posteriori error estimate for my minimizing movement schemes. Namely that the error or the difference between the exact and approximate solution is controlled by, well, something that has to do with data. This is only telling you that there's features in your grid that in your F that may not be captured at the level of the grid F, the grid or the partition. The important thing is that one of the things that bounds this error is this quantity over here. Well, you know the taus, those are the time steps, and you know the e's. Once you have your approximate solution, they're completely computable. So this is something that you can compute, and then you can make a decision. Say, okay, if these are good, then you can sign whatever you need to sign and say, okay, my solution is good, right? Because this is an upper bound. If not, maybe you need to do something else, or maybe you can use these quantities to choose your time step adaptive. That's why we call this a posteriori estimate. It is also interesting that, say, for instance, if I take out a tau out of this sum, say as the max, if I compute only the sum of tau times E, that can be controlled from above in terms of data. And so as always, under some conditions, essentially assuming that I start with something from initial with finite energy, we can get the a priori estimate that's the error is of order tau to the 1/2, which, if you remember, the energy solutions were in H1, which means they were Helder 1/2. So this is an optimal error estimate, right? Because approximation theory tells you that being Helder 1/2 is equivalent to being able to approximate it with order 1/2. by piecewise linears or constants. Okay, so this is the a very quick review of the error analysis for the classical case. And now, what are the essential points that we needed here? Well, we needed a positive quantity that depends only on the computed approximations. Those are your error estimators, if you will. Now, you needed to show that your interpolant solves a perturbed gradient flow. So the same evolution variational inequality that the exact solution solves, but plus something else, some perturbation, where this perturbation is the estimator that you construct. And finally, to be able to get from the inequality with two functions to the one with one function, your interpolant needs to be a convex combination of the nodal values. So now let's see if we can do that in the fractional case. And so we're going to do essentially the same. We had this is the optimality conditions for the fractional minimization movement scheme. We can write it as a variational inequality. We can throw everything to one side and see that everything here is computable because it only depends on the discrete solution. And on top of that, it has a sign. Right? So now this is going to play the role of our perturbation. And indeed, say if you were now to try to follow the steps of the classical case, you would end up needing, once again, that this U hat is a convex combination of the nodal values. And if you recall, we defined that as a linear combination of some functions phi I that were those that whose Caputo derivative was piecewise constant, and one in one interval and zero in the others. So these functions, well, here I have some depiction of how do they look like. They look weird, but such is life. Their support is not local because these are non-local derivatives, so it's not expected that they are going to be locally supported. They look, say, for instance, quite different from the usual hat basis functions that are the basis for piecewise linear interpolation. However, um, you can show that these functions are all non-negative. I mean, that's kind of seen from the picture, but yeah, you can prove that. And on top of that, they all add up to 1. So much as in the linear case, this interpolant, the one that is interpolated using these functions, is again a convex combination of the nodal values. So much as in the classical case, you can show that this interpolant then using this convex combination of the nodal values satisfies this evolution variational inequality, which is modulo the green term, exactly the same that the exact solution solves. And well, you have an extra perturbation. So you can compare the two inequalities once again and get an a posteriori error estimate. Same way that you did when we computed uniqueness. And once again, this is data, don't worry about it. This is telling you there's some quantity that you can compute once you have the approximate solution that controls the error. And that can guide you in the construction of your time step scheme or your time steps. From this a posteriori error estimate, we can also get an a priori one. So let me skip some details that we just mentioned that, okay, once again, we need to use the fact that this U hat is a convex combination of nodal values to get an a priori estimate of the form that no matter what partition I use, I can get an error of order the maximal time step to the power alpha over 2, which, if you recall, we also showed that energy solutions were were Hölder continuous of order alpha over 2. So this error estimate is optimal in the term of in the sense of the regularity that we have. Okay, so this is, if you will, the second big result that we obtained with Wimbo. So once again, we were able to extracting the essential features of the classical case, extend this to the fractional case. and in a way that is, for instance, optimal with respect to the regularity that we have. Let me show you a few numerical illustrations of this scheme, so of the fractional minimizing movement scheme. The first one is a very simple one-dimensional linear example. So just think of your, yeah, the function is it takes it's from R to R, and your energy is lambda over 2u squared. You start from 1. And we take this very simple example because we know the exact solution is just some expression related to the beta-Kepler function. To be able to compute the error, let's take a uniform time step, and let's measure the error at the final time step, just as a measure of the L infinity error. And it turns out that the convergence rate is of order tau to the alpha. So twice as good as what our theory suggests. We have some partial explanations for that, but I mean, it wouldn't be surprising that our theory is not completely sharp in this case, right? Because our theory is supposed to handle differential inclusions in Hilbert spaces, and here I'm essentially trying to kill a mosquito with a bazooka because this is a one-dimensional example that on top of that is linear. So maybe if we complicate our example a little bit, for instance, if we consider this energy, which is not everywhere defined, but still it's convex. Notice that if you were to try to compute the subdifferential at 0, that's empty. We consider that as a gradient flow with this energy still in R. Then, and you start from 0 because this is a problematic point. The rate still seems to be tau to the alpha. So still, our theory, of course, this is not a contradiction with our theory, but our theory doesn't seem to be super sharp in every case. Just as a last example, let me show you how you can do adaptivity using this posteriori estimator that we constructed. The idea is that, well, you choose a tolerance. Now you're going to try to choose the time steps. So you're going to move in such a way that your estimator at each subinterval is of order epsilon squared. If you can guarantee that by choosing the time step, then your total error is always going to be of order epsilon. So just for illustration, let's say that I take some tolerance to be 10 to the negative 5. I run this strategy. Then my adaptive solver is going to need about 9,000 time intervals, and it gets done in 2.5 seconds. In comparison, if I was going to do a uniform time step, if I want to reach a similar tolerance, the size of the time step needs to be, what, 6 to the 6 times 10 to the negative 6. So that I need 160 something time steps. And that gets done in about 160 seconds. So there's a quite stark difference, even in this very simple linear example. There's quite a bit to be gained by using adaptivity. Yeah, and this is how the time steps would look like as time increases. It is known that, say, these problems have a weak singularity at t equals 0. So at the beginning, you need to do very tiny time steps to capture the features of the solution. After that, the solution is smooth, so you can take larger time steps. Okay, so I've talked for too long, so let me just recap what I presented to you today. I gave you a discretization of the Caputo derivative over any time grid that has suitable properties. With it, I was able to show existence and uniqueness of energy solutions to fractional gradient flows. For this discretization, I gave an a posteriori error analysis, so I constructed a quantity that is computable, that controls the error. I gave an a priori error estimate that doesn't assume anything on the solution other than what is natural. And this estimate seems optimal given the regularity that we know of the solution to this problem. Of course, there's much more to be done. For instance, try to explain why the experiments that I showed you have a rate of tau to the alpha. And we have some partial answers to that, but we need to explore this a little bit more. Um, the theory of gradient flows allows also for the energies that are not only convex, for say, but also lambda convex. You can have Lipschitz perturbations. Um, you can replace the subdifferential by a general maximum monotone operator that is not necessarily a subdifferential. You can try to extend this theory to Banach spaces, but yeah, that will be a little bit more complicated. And of course, if you want to really do numerics of PDEs with this technique, you need to discretize in time. And with that, I will finish. Thank you.
All right, thank you very much, Abner. Very interesting talk. I think we have questions for a couple of quick questions.
Yeah, Abner, thanks a lot for your talk. Especially, I enjoyed the part you use a numerical technique in the proof of existence. That
Oh,
was
yeah,
good. So, if in the applications you're thinking of, what value of alpha is physically meaningful, and am I correct in that the problem get harder as alpha goes to zero? Would you mind commenting on those?
well, okay, so these are questions for applications, right? I mean, so what value of alpha is physical here? That's, I guess it would depend on the application. In fact, I mean, I don't know what people say that should be the value here.
If I may, I would comment that I
Yes.
have done some work on evolution of particles in fluid flows. And there you have these memory effects and it's modeled with a fractional order derivative of order 1/2. So at least in
Okay.
1/2 is the case where in fluid dynamics it exists.
Uh, yeah, well, I mean, I don't know how. Okay, so let me say something. Let me take what I'm going to say with a big grain of salt, because there are some people that say that the actual Navier-Stokes equation should have a partial derivative in time of order 2/3, because that makes it more accurately describe the Kolmogorov-Berlin scales or something like that. But again, that's what they say. uh, yeah, so I guess it depends on the application. And you also asked why that these problems get more difficult at alpha.
Yeah, is it alpha closer to zero or alpha less closer to one that's hard? Because your estimates had to the power of alpha, so I'm just wondering if it
Oh, well,
which
I mean,
limit is the harder one?
well, when alpha goes to zero, you don't have an evolution equation anymore, right?
Right.
So, I mean, if there is some consistency, the equation only becomes u minus Laplace u in that case. So then there's no time to be discretized. So I guess that's why those estimates behave that way. I guess you're not just applying the wrong technique to the problem in that case, I guess.
Fair enough. Yeah, thanks.
Okay, are there maybe one more question? All right, if not, thank you, Abner, again. Very interesting talk. And thanks for spending the time to tell us